Let's talk about aromatic hydrocarbons. Now, this is actually kind of a misleading title because we're not going to be talking about all kinds of aromatics, which is a whole class of hydrocarbons. We're really just going to be talking about one aromatic, the most important aromatic, which is benzene, C6H6. So organic compounds that has a structure based on benzene, that's kind of misleading, but great for Chem 30. We're going to go with that. Or a benzene-like ring. At one time, they were organic compounds with an odor or aroma. At one time? Yeah, that doesn't make sense. Many of them have an odor or aroma, which is the reason why it's called aromatics. So benzene has a really interesting history. It used to be this kind of big problem or thing that perplexed chemists for years. And the reason why it was confusing for chemists and they were mystified by benzene is because they had these really kind of interesting properties or weird properties that didn't make a ton of sense. So, for example, there's no empirical evidence to support the idea of a double or triple bond. It does not react with hydrogen, but it had the formula of C6H6, so it's like it's missing a bunch of hydrogens. It looks unsaturated based on the formula, but it doesn't do normal reactions that an unsaturated hydrocarbon like an alkene or an alkyne would do, which is weird. X-ray diffraction indicates that all carbon-carbon bonds in benzene are the same length, which again is really strange based on the formula. Double or triple bonds are actually shorter than single bonds, and so you can see it when you look at X-ray diffraction that there are bonds that are double or triple bonds that are different than other bonds in an alkene or an alkyne, but benzene doesn't show that. All of the bonds in benzene turn out to be the exact same length between carbons, which was very strange based again on the formula. And evidence from chemical reactions indicates that all the carbons in benzene are identical. So every single carbon is just as reactive as other carbons in benzene, and that each carbon is bonded to just one hydrogen. So that seemed weird, right? How could we have every single bond be the same, every single carbon be the same, but still accomplish 6 carbons and 6 hydrogens in the structure? So here's the structure for benzene. What it is every single carbon has a double, or every second carbon, sorry, has a double bond, right? So double bond, single bond, double bond, single bond, double bond, single bond. But that doesn't match what you just learned, that all the bonds were the same. So it actually is both this structure and this structure at the same time. You'll notice that what's happened between here and here is that I have a double bond that's moved from this spot to this spot to this spot, and this spot to this spot, making this structure here. This is called resonance, in that I have 2 possible ways that I can draw something that actually works in terms of where, let's say, double bonds are. And when I do that, it's actually existing as both of these structures at the same time. So these electrons that are the double bond electrons are actually moving the whole time from one position to another position. It's actually kind of like in this like cloud of electrons where it's existing in all of these places essentially at the same time. So because I have these 2 structures at work, it has resonance, and these bonds as a result are actually strengthened and more stable than a normal double bond. So how we represent this resonance structure and the fact that it's both of these structures at the same time is we can actually kind of draw this special diagram which shows the double bonds as this circle, which just kind of shows that these double bonds are delocalized. They're not in just one of these or in 3 of these positions, but they're in all of these positions at one time. In other words, it's both of these structures at the same time. Is this confusing? Probably. So let me just kind of sum it up, that in benzene, it has 3 double bonds, but those double bonds are actually existing between all of the carbons at the same time. They're what we call kind of delocalized electrons. So we have this resonance kind of way of representing benzene, of saying, hey, here's our double bond electrons right here as a circle in this benzene structure. So we have a special name for this, and that is a base name of benzene. All right, so that's what we call this, is benzene. So first of all, recognize you have a benzene structure and not a cyclohexane ring. It's not cyclohexane because I have those 3 double bonds. It's instead benzene. Number the carbon atom in the parent hydrocarbon, the benzene ring. So that position number 1 is assigned to the branch alkyl group that comes first alphabetically, just like when I was doing the cyclos. Then number in the direction that gives the rest of the branches the lowest number possible. If you have a tie for that, then at the lowest total possible. Name branch position and size of the branch is the same as in alkanes. End with the parent hydrocarbon name benzene. If you have to name benzene as a branch, which is a weird kind of situation where you couldn't name the branches because it has branches coming off of branches. So you can't have benzene as the parent chain. You instead have to make it as a branch to name it properly. I'll show you an example in a bit. Then benzene as a branch has the branch name of phenyl, P-H-N-E-Y-L. And it's named like any other branch, okay, but it is phenyl. You're going to see an example of that when we get to D. All right, so if I take a look at, for example, A, I recognize that, hey, here I have benzene. I have one methyl group. So this is simply one methyl benzene. Or if you wanted, you could just say methyl benzene, and that would be okay as well, because obviously if I have a methyl, the only place it could be is carbon number 1. It gets priority because it is the only branch. All right, I've got 2 branches right here, and it's both ethyls. So I would have carbon 1 and carbon 2 of my benzene. So this is 1,2-diethyl benzene as a name, right? Ethyl, ethyl, 2 ethyls on that benzene. If I go 1,2 or 1,2, it doesn't matter. Now for, oh, I did C first. Whoops. Now we go to B. Where should we start? Should we start on the methyl group or on the ethyl group? And the answer is we want to start on the ethyl because that is alphabetically first. So that's carbon number 1. And now we figure out, do we go clockwise or counterclockwise? And going counterclockwise gets us to the methyl on 3, while going clockwise gets us to the methyl on 4. So this is the correct numbering: 1, 2, 3, 4, 5, 6. So I have 1 ethyl, 3 methyl benzene. Oh. Okay, for D, here's the reason why I need to make the benzene the branch. This is not a propyl. Propyls are carbons all in a row, 1, 2, 3 in a row. Instead, what I have is I have this attached to the middle carbon of these 3 carbon chains. So I can't name this branch in a way that you guys know how to name it. So what I actually do is instead I make this the parent chain, 1, 2, 3, and then I call this 2-phenyl propane. So again, the fact is if I treated this as the parent chain, the benzene, then I have a branch coming off of a branch, right? I got a methyl coming off of an ethyl. I can't name that. So instead I make the 1, 2, 3 carbons the parent chain, and then I call this a phenyl. So how do you tell? Well, if it's attached to the middle of a hydrocarbon chain, right? If the benzene is on the middle of a hydrocarbon chain, then the benzene is going to be the branch. So this is 2-phenyl propane. I could also just call this phenyl propane because there's no way that it could be anywhere but on carbon number 2, or else it would have a different name, right? So 2-phenyl propane is that one for D. There's another way of naming this stuff or numbering it, which is kind of a neat way to do it. We're not going to do a ton of this, but you need to be able to read the name and come up with kind of the structure for it, but we don't often do the naming this way. But it's ortho, meta, or para, which is sometimes just shown as an O, an M, or a P. And what this does is it actually represents when I have 2 groups that are the same, okay, 2 branches that are the same off the benzene, the position of those 2 branches. So if they're side by side, we call that ortho. If they're kind of, what would you call it, positions 1 and 3, then it's meta. And then if it's on opposite sides of the benzene, so it's 1 and 4, we call that para. Okay, so 1, 2 is ortho, 1, 3 is meta, and 1, 4 is para. The way I remember this is I just think of like OMG, but I instead say OMP. Okay, and then that's how I remember ortho is side by side, meta, para. You can remember ortho is side by side because of orthodontics, where you want your teeth all side by side and neat and tidy. So here I have my 2 groups side by side as well. All right, so these examples above, 1,2-dimethylbenzene, right, would be the normal name for this. Instead, we call it ortho-dimethylbenzene or O hyphen dimethylbenzene. This would be 1,3-dimethylbenzene or meta M-dimethylbenzene. And then here, there should be a space here, by the way. 1,4-dimethylbenzene or para-dimethylbenzene for that one. Okay, so that's kind of how we do that naming, a little bit interesting. So we could actually name this one in that way. F would be interesting to do in both ways. I can't do that for E because I have more than 2 branches. I got 4 branches here. So how would we name this sucker? By the way, well, we could either start, you got to figure out a way that gets the lowest numbering possible. So the way that we could do that is we can get branches on 1, 2, and 3 by going either 1, 2, 3 or 1, 2, 3. So that's where I have branches side by side, right? So that would be the best way to start out. So I go 1, 2, 3, 4, 5, 6. So the naming for this would be 1, 2, 3, 5 tetramethylbenzene. Now, again, remember to make sure that actually is a benzene. You're going to see examples coming up here where it's just a cyclohexane and it's trying to trick you. Okay, and then it has like, you know, this, and you're trying to figure out, oh, well, how do I do this? And then you accidentally give it the name of benzene. This is not benzene. This is cyclohexane. It would be 1, 2, 3, 5 tetramethyl cyclohexane. As soon as I put the ring in there representing the 3 triple bonds, right, the benzene resonance structure, well, now it's benzene. This one, I can actually use my OMP kind of naming for this. So I have 2 propyl groups. So I could name this as 1, 2, 3. So 1, 3 dipropyl benzene. Or if I wanted to get fancy, I could name this. I'm just realizing right now that I did this wrong and that these should not have a space in it. I feel bad. All of these should be spaceless. So when I said, oh, put a space in there, that's totally incorrect. It should have the absence of a space. I feel silly. All right, anyways, going back to this example. 1,3-dipropyl benzene. This should be meta dipropyl benzene, okay, as a other name that I could use. Or instead, M-dipropyl benzene would be another way to name this. So that is essentially aromatics. Now you got a bunch of examples going through alkenes, alkynes, aromatics, and then actually naming which type it is. So let's review the different hydrocarbons that you know so far, right? So in organic compounds, so far we've dealt only with hydrocarbons. So only things that contain carbon and hydrogen. We've learned about 2 different types, aliphatics and aromatics. So aromatics, as far as you need to know in Chemistry 30, is things that contain this benzene structure, right? You now know how to identify. It could either look like this with the circle in the middle, or it could have, you know, something like this with the 3 triple bonds in a cyclohexane arrangement. Okay, for aliphatics, I have 3 different types. I have alkanes or cycloalkanes, alkenes or cycloalkenes, and alkynes and cycloalkynes. These are unsaturated when I talk about alkenes and alkynes, which means that I can react these with hydrogen or other stuff in order to do addition reactions. You're going to learn about that in the next lesson. And then when I have cycloalkanes or alkanes, these are considered saturated, which means that I cannot do addition reactions with them. Okay, nothing else can add because all of the carbon-carbon bonds are single bonds already. So that's where we're at so far in our study of organic. Is we've covered hydrocarbons. We're going to do hydrocarbon derivatives soon, which means we're adding things besides carbon and hydrogen. We've covered aliphatics and aromatics. Aliphatics just think of as not aromatics. Okay, so it doesn't have benzene. Aromatics has benzene. Aliphatics, I've got 3 types, alkenes, alkenes, and alkynes, and then cyclos are in there as well. Okay, well, that's it for aromatics and then reviewing what you've learned about hydrocarbons so far. Have a good rest of your day.